Alright, so a little background into what we are going to be doing today. So we are going to be talking about the LZ algorithm. I will try to, it's a very technical session, let me put it like that. It's a very technical session. And it's one of those things I figured, everyone has related to the software engineering part or anything that involves like engineering in technology. I figured this is a very important topic that we should like try to like get a little bit of what happens behind the scene. So we are going to be talking about LZ on the web, scaling the unscalable, LZ on the web, scaling the unscalable. And a little bit of background, LZ stands for impressive. I don't know if you can hear me very well. LZ stands for impressive. So what happens behind the scene is you see like you've worked with as many media files as possible. Say you work with videos, you work with images, you work with tests. I don't know if you get what I mean. What we are going to be discussing today is the origin of why probably an image in PNG and one in JPEG, why one is clearer than the other, or why you are able to like send large body of text in a very compressed format. So LZ is a compression type, and that's what we are going to be discussing today. At the end of our discussion, we are going to have like a little like code work to like evaluate together. Alright, so my name is Daniel Olabemiwo. Well, visit me. This is like a general introduction I give almost everyone. I have a surname that almost no other one have in the whole of Nigeria. So you can just Google my name. Yeah, and this is Daniel. Okay, I am a software engineer at Spitch AI. And what we do at Spitch is just pure machine learning algorithms and everything around LLMs. Think of text to speech, speech to text, speech to context, speech to intent, almost anything you can figure around speech. And usually we work with a whole lot of data. So these are like one of the things we literally take note of day to day. And this is what I literally do day to day at work also. Also, for as many that with their PC, I don't know if you can like check out this GitHub repository. This GitHub repository contains like the code work we are going to be using today. Very expressive, very minimal, something like everyone can understand. There is okay, I was able to write the entire code work we are going to be using today. Probably you are writing JavaScript, you are writing Rust, you are writing Python. So it's an open source code base that I think everyone can check out. All right. So the paradox, compressing what has already been compressed. All right. So for example, let's try to imagine you are sending a body of text, say like 50,000 words. No characters, 50,000 words, and then you need to process those body of text, and you need to send it at high speed rates. I don't know if you are trying to like imagine what I'm talking about. You need to send it at high speed rates. You need the text to remain how do I put it? To remain in its natural state. Let me put it like that. That is, nothing gets missing in transit. Nothing gets missing in transit. Or try to imagine you are trying to send like say like a terabyte of media files. Say like a video that is like say like 24 gig, and you have those videos. Say like you have like 10 of it. Gradually from 24 gig, you are already at what? 240 gig. I don't know if you get what I'm trying to talk about. And then you want to send something like that over the internet or over like a network. And then there's this issue that we usually have. Say like we we send media as one. I don't know if you've experienced it. For as many that have tried to like say like, oh, you're uploading media files to say your backend server or something, you tend to send it as one. And this work in a very small situation. In a very small situation, like you are sending say like two megabytes of image or something, say like uploading profile picture. Oh, those are like very minute. But then when you start thinking of sending like a video file that is say like 2 gig, and then if you have this problem of once there's a break in connection or once there's a break in internet, hope you know that what you've done is literally void. If you are sending like 2 gig of say like a video over like say like a REST protocol, and there's like a break in transmission, that means you have to restart, and then they introduce technologies that literally led us to like, oh, now you can upload things in chunks. You can upload things in chunks, maybe like 100 MB, 100 MB, 100 MB, 100 MB, 100 MB. So like I said, is like the behind the scene of what literally powers being able to like move things in chunks, being able to compress things in chunks, being able to compress things and also like being able to like move them seamlessly. So that's what we are going to be looking at today. All right, so this is like background story of like, oh, how the LSED algorithm came alive, the two guys that brought about the LSED algorithm. And like I mentioned earlier, what do you say? Okay. Like I mentioned earlier, LSED algorithm is like the basics of almost any compression tool you use today. For individuals that have like Windows PC, I know we've used things like say like WinRAR or like 7zip, all those. So this is like, oh, what powers those technologies itself? The ability to like find patterns in the media you are trying to like send over like a network or something, being able to like find pattern and being able to like replicate it easily. So this is like I mentioned, what powers like say like virtually 95% of like web compression technologies we know today. Your 7zip, your PNG, your okay, JPEG is lossy, but your PNG. So probably you've noticed that, oh, if you save a picture in PNG and you save a picture in JPEG, there's difference. I don't know if we noticed that. Oh, if you try to like save a picture in like PNG and try to like save a picture in JPEG, there's like lot of differences. How I'm going to point it out to us is, if you try to like save a picture on the internet and you right click and probably like you open the media in another browser, there's a possibility that the media you've opened, oh, they give you like a clearer quality as opposed to you right clicking and downloading the image straight up. So the image you are seeing straight up, say like, oh, you are scrolling through Facebook and you saw an image and you decided to like, oh, just right click and download immediately. There's a possibility that image is like a JPEG image. But when you open a new tab, you notice the file structure, possibly it has moved to say like WBF or PNG itself. What happens is the JPEG image you are looking at is a lossy compression technique. So there's a lossy compression technique and there's a lossless compression technique. I don't know if you are still following. There's a lossy compression technique, there's a lossless compression technique. What happens with the lossy compression technique literally is, oh, you are still going to see the image, but there's like reduction in quality. So that's what happens when you request that, oh, please, probably like send the image as a document. Because WhatsApp won't pass it through a lossy compression technique. What happens with the lossy compression technique is, oh, they just allow you to at least just see the image. That seeing of the image is the most important thing. Not like, oh, how sharp it is, or if they are still like pixel perfect. I don't know if you get what I mean. So that's like a lossy compression technique. Oh, they just have put it, the main focus of the lossy compression technique is, oh, you're able to see what you are looking for, but it might not be the best quality. But what happens with the lossless compression technique is, oh, even when you want to reduce, say, like the price size, the quality must remain. The quality must remain. So that those are like the two main difference. And like I mentioned, the outside compression is like the origin of like very popular compression tools we use today. The 7-C, the G-C, the Wera, the PNG, GIFs. Yeah, all right. So we are going to start with LS77. So under the impressive compression group, we have like two main divisions. We have the LZ77 and there's the LZ78. It might not make like, you might be thinking, oh, where will this happen, or what leads to this? But over time, probably you grow in your role or something, and you start to like, make like core technical decisions as to, say, maybe you are building like a media application, or you are building like a test heavy application. So for example, if you are doing something like Microsoft Word on the web or something, I don't know if you get, those are like, very core things that you take note of, or ensuring like, while you are dealing with every media, how do you ensure like, they don't affect your web performance, they don't affect like almost everything else. They don't affect everything else. So that's like some of the reasons why you need to like, get note of all this technology. So like I mentioned, the S77, for as many that probably they've gone through data structures and algorithm, the time sliding window should be like a very familiar time. The time sliding window. So I try to like show us like a picture here to like understand like what it does. Okay, so you can see the Google Developer Group Ilorin is a group situated in the city of Ilorin for developers. You can see like the sentence. So literally what the LZ77 does is, it looks for words that exist before. So you can see like the word THE, which is located also here, existed before. You can see the word group existed in both places also. You can see the word developer exists in both places also. Alright, and so what it does is, when it gets to developer here, instead of writing developer behind the wood, instead of writing developers, what it literally does is, it looks for the previous word and then represent it with those notations like I noted before. So so the 63,6, the 56,3 is what we can see as the R, E. And what it literally does is, the word THE, it counts between the first THE and this second one. I don't know if you get what I mean. If you can't display the character count between the first THE and the second one is 56. I don't know if you get what I mean. Then the 3 is like, THE stands for 3. Like 1, 2, 3. THE. So that's what it does. If you see the word Ilorin, that means the difference between the first Ilorin and the second one is like, if you count IS space A space GR up to this Ilorin is 63. And then the word Ilorin like is a 6 character word, and if you add it together, that's what leads to 63,6. That means if you have like a 50,000 word and you have Ilorin like scattered all over, that means it will keep keeping the notation of the difference from the first one, and then the count. So that's like how the LZ77 works behind the hood. And you can see, instead of keeping like a six character word, which literally can be like 4 bytes each. It is a lot of mathematical stuff, and it's very interesting. Instead of writing Ilorin continuously, it represents it with that notation. And you can think of it in the terms of, if you have 50,000 words, you can think of it, you can think of it in terms of, if you have 10,000 words, or you have 50,000 words, and you can think of it, oh, instead of having those words like straightened up, they have it like, oh, broken down into chunks. Now, this breaking down into chunks should give you an idea of now how 7-zip, how you are able to compress something like that is like, say, like 8 gig into like 3 gig with all these compression stuff. This is like, oh, one of the things they do behind the scene. Even with your images, with your videos, this is like what happens behind the scene. Being able to like go from that 6 digits, this is just this notation, and then think of it in terms of scaling, like, oh, if you have Ilorin scattered across 10,000 watts, and oh. So that's what happens with the LZ771. Okay, this is like mathematics, which might be a little bit boring. Okay, all right. So it has like 3 main components, like I mentioned. The search buffer. Okay, so this is the search buffer. The search buffer is what goes from each word to each word. Oh, is the one that goes from the Google develop. Is more like, oh, when you are reading stuff. That's like the search. That's like the search buffer. The look ahead buffer. The look ahead buffer is what traces it back to, oh, we've seen the word Ilorin before. Let's relate it with the previous Ilorin we've seen and represent it with the notation. That's the look ahead buffer. And the sliding window is, how do I explain sliding window? But the sliding window takes like, oh, say like in an entire like body of work, the sliding window can go, say, like a sentence by sentence scope to like understand like, oh, what is happening like between each sentence. Sorry. All right. Okay, so this is like what's the name? This is like the man that brought about SZ, and this is an intuitive code work for as many that want to like really like just try it out. Like I mentioned, the GitHub link I shared earlier, this is like the implementation that brought about it. This is like the algorithm like definition that brought about it. Very intuitive, and yeah, we can literally check it out at the end also. All right, the LZ78. Okay, so in the LZ77, don't forget we had the buffer, the search buffer, and then the sliding window. Okay, so the LZ78 that we are going to look at, we had the buffers and every other stuff. In the LZ78, we have what we call a dictionary. And we are going to run through this together as much as possible. And don't forget the notation we had in the LZ77, where we have the number of characters and the jump. The jump is like the difference between the first word and the word you are trying to reference. Okay, in the LZ78, we have like a dictionary of tokens. And what this dictionary, what it literally does is, you can see this word I tried to like divide. I don't know if we can see this word. Oh, and what happens is, oh, when we start here, we see the word A. Remember, we've not seen A before. So that will be like index 0 and then A, which is the last character. You can see like, oh, the entry is A. Don't worry, over time we understand. Then we have B. We've not seen B before, so we have to register B as 0, character B, and you can see the index as 2 and the entry as B. We've not seen C before, so we can see like, oh, we are going to have the index 0 and the character C, and then you can see the entry as C. Okay, where it gets interesting now is, we've seen A before. I don't know if you understand. We've seen A before. So because you've seen A before, we are going to look for the next letter after A, which is C. So now we have A and C. I don't know if you get what I mean. We have A and C. We've not seen A and C together before, right? We've seen A before, we've seen C, but we've not seen A and C together. You know, there's like B between A and C. So because we've not seen A and C together, we are going to record it here as the first letter in AC is what? The first letter in AC is what? A. The index of A is what? You know, we've seen A, and the index of A is 1. I don't know if you get what I mean. We've seen A, and the index of A is 1. So we are going to write it as 1. The last character in AC is what? The last character in AC is what? C. So we are going to record it as C. So what we are literally doing is the index of the first letter and the character of the last letter. The index of the first letter and the character of the last letter. So you can see like the index of A that we've seen before is 1. And then the last character is C. So you can see that we record it as what? AC. So we are going to go to the next one. We've seen B before. We've seen A before, but we've not seen BA. Again. So what's the index of B that we've seen before? What do you say? B before, and we've seen A before, but we've not seen them together before. So like I mentioned, out of the two, the index of the first letter and the character of the last letter. So the index of B is what? 2. The last letter is what? A. Now that's what led us to having 2, CA. And then we continue like that. We've not seen D before, so we are going to record it like that. We've seen A before, we've not seen A and D together. So that was what led us to having AD here. And then we are going to record this as the index of the first letter, which is A, which is index 1, and the last character is D, which is like character D. And then for things like BC, we've seen BC before, we've seen B, we've seen C, we've seen B and C together, but we've not seen B, C, and E together. So that's what led us to having BCE. Again, the index of the first letter is what? B. The index of the first letter, the index of the first letter actually now, instead of going to B, we are going to record it as BC, because BC already exists. So that's why we are going to have 6, which is, if you look to index 6, you are going to see the BC. And then we are going to have the last character E. So continuously, you can continue and continue like that. And gradually, you can see how we are able to build like a SS78 dictionary. An SS78 dictionary. Let's go to the next one. Next slide. Next slide. Our time is up. All right, but we try to like run through this a whole lot, so you have to like just keep going, like I tried to explain earlier. Now you're able to like identify like, why some images appear like, they just want you to see what you have, and why some images, even despite compression, you're able to like have those images in the clearest format as possible. Let's try to move. Sorry, next slide. Next slide. Interesting. Next slide. Okay, JS performance. Next slide. Browser limitation. Okay, network constraint. Just stop. So, like I mentioned. Okay, just stop there. No, just go back. Go back. Yeah, just stop. So, like I mentioned earlier, when you start dealing with very heavy files, say like videos, images, or a lot of tests, say like you have like 50,000 words and stuff, like you're not thinking of like, how best do we ensure like these implementations that, or this computation we carry out on the web, say on people's browser, how best do we ensure like, we take note of performance and we take note of every other stuff. Next slide. Sorry, our time is up. Yeah, just keep going. Yeah, and these are some of like ways that probably we've noticed, especially when you are dealing with other applications. Probably you've noticed that you are able to like run things smoothly, or you're able to like go through the application smoothly. Next slide. Just keep going. Just keep going. Just keep going. Just keep going. Okay. Or go back. Yeah. Okay. So like I mentioned, the SZ algorithms are elegant and powerful. Google itself has developed like algorithms like I've forgotten the name of the SZ algorithm. There's been like various improvements. They've been able to like combine it with the Hoffman encoding. Just a whole lot of technology also have like comfort from just like the SZ algorithm itself. So I think this is the end of like quick explanation on LZ77 and LZ78. Thank you.